Everyone thinks fog is just clouds that fell to the ground. They're completely wrong. Fog isn't a cloud that descended. It's something far stranger. A cloud and fog are made of identical water droplets suspended in air. The only difference is where they form. But that detail unlocks a puzzle that stumped physicists for centuries. How do trillions of droplets just float there? Why don't they fall? The answer lies in a place most of us never think about: the space between atoms. When water evaporates from a lake or ocean, it becomes invisible vapor. Billions of molecules scattered through air, bouncing randomly in every direction. They're so small, so dispersed, that air molecules don't even notice them. But then something shifts. Temperature drops. Maybe it's evening. Maybe a cold front moves in. And here's where physics gets generous. Those water molecules start colliding with dust particles, salt crystals, or bits of pollution floating invisibly in the air. These tiny specks are called condensation nuclei. A water molecule hits one of these particles and sticks. Then another, and another. Dozens cluster together, forming a droplet so small you couldn't see it even under a standard microscope. We're talking about sizes measured in microns, 1/1000th of a millimeter. At this scale, the rules of physics change. A raindrop is roughly 100 microns wide. These fog droplets, about 1 micron. That means a fog droplet is 10,000 times smaller in volume. Smaller means lighter. But here's the crucial part. Smaller also means something else entirely. Air resistance becomes king. When an object falls, gravity pulls it down, but air pushes back. For large objects like a raindrop, gravity wins easily. The droplet falls at about 9 meters per second. It hits the ground. But for something 1,000 times smaller, the math flips. A fog droplet experiences so much air resistance relative to its weight that it barely falls at all. Its terminal velocity, the fastest it can possibly fall, is less than 1 centimeter per second. Some fog droplets fall even slower. And here's what matters. The air around them is always moving. Even the gentlest breeze, a current of air you'd barely feel on your skin, can push a fog droplet sideways faster than gravity pulls it down. The droplet gets caught in invisible currents, eddies, and swirls. It drifts. It floats. It hovers. But there's another force at play, one that most people don't know about. It's called Brownian motion. Invisible air molecules are constantly bombarding these tiny droplets from every direction like a microscopic hail of bullets. The impacts push the droplets around randomly. This jostling, this quantum-scale chaos, keeps the droplets suspended. They don't sink. They bounce around in place, buffeted by forces so small and so numerous that their effect is to simply hold them up. It's not magic. It's just physics at scales we rarely experience. So fog is a delicate balance. Gravity pulls down, air resistance pushes back, wind pushes sideways, molecular collisions jiggle everything randomly. These forces don't cancel out, they dance together. The result is something that shouldn't exist by everyday logic. A cloud you can walk through. The moment conditions change, temperature rises, or humidity drops, those droplets evaporate back into invisible vapor. The fog vanishes. But it was never really there in the way we think. It was always a negotiation between forces, a temporary armistice between gravity and air. Understanding fog teaches us something deeper about the world. We live in a universe where size matters profoundly. The same water behaves completely differently at different scales. Small enough and it floats. Large enough and it falls. There's no single answer to why things fall or float. Next time you walk through fog, you're moving through trillions of tiny negotiations between physics and chance. Each droplet is held aloft by forces so precisely balanced that the slightest change, a gust of wind, a degree of warming, shifts the entire equation. Fog isn't a mystery anymore, but it's still something worth marveling at. Because it reminds us that the ordinary world runs on physics we can understand if we're willing to look closely enough. Subscribe so you don't miss the next everyday enigma waiting in plain sight. Subscribe so you don't miss the next everyday enigma waiting in plain sight.